fellow students, anonymous strangers who happen to wander across this video. This is a presentation. I'm Joshua Goossen. I'm in the CS 6263 course in spring 2019. This is a presentation on an experimental security analysis of an industrial robot controller. The original paper was by David Quarta, Marcello, Pogliani of the other contributors from the Dipartimento di Elettronica of Milano, Italy. And this is a presentation for Georgia Tech. I found this to be a very interesting paper, and I myself am coming from an industrial and a industrial systems and also computer science background. And this is a very cool way to really merge and look at both industrial systems and computer information systems, in addition to that from a security standpoint. And that's really what David Quarta sets out to do throughout this document. Why is this of interest? If you're not a computer science person, if you're not a industrial systems control person, or maybe not, you don't even work at a manufacturing plant, this is maybe still of interest to you, because all the products that we receive or energy directly impact us through these systems. There are 1.3 million robots in factories. That was the forecast for 2018. That's probably since grown. The robots are growing in complexity and number of components, and what that means is that all of these robots and all of these systems in manufacturing factories and all of the people that work in those factories and receive products from those factories are at risk. Also, the scope of what an industrial system or a manufacturing factory has been growing. We're now seeing more and more integration with other vendors, with other factories, potentially with other workplaces. And so the scope of these, exactly what a manufacturing system is, and therefore what the impacts could be, has increased significantly. As an example, I think this particular document refers very frequently to Industry 4.0, and this diagram on the lower right shows exactly how these systems are becoming more and more integrated over mostly the internet. So what is it that David and all of these individuals are after? They're trying to build and understand robot architecture, because they want to maybe have fun and attack it, but also prevent the bad attackers and bad situations from happening. So they build also a model of attack classes or different types of threats. They look at the vulnerabilities, and they try to look at industry-specific challenges to implementing either countermeasures or making improvements. The way that they do this is, first, I think they reference a number of surveys that were done. I don't believe they were directly involved in all of them, but they kind of take a survey of the land, look at the overall industry threats, and try to get an understanding of what the industry and what type of risk are associated with the industry at a very high level. They then look at system architecture. This is where the computer systems and the industrial systems knowledge comes into play. They then develop from that an attacker model to try to understand, okay, if somebody wanted to bring the system down, what do they need to know? What are their interests? And then I think what is most interesting here is that they actually perform security pen testing of these systems and then propose future directions. And that's mostly what this document is going to cover. So the high level, they look at, again, threat scenario assumptions. This is a priori thinking about the problem. They're looking at, and I think for the most part, a lot of this would be textbook for anybody taking a cyber physical security course. They're looking at threat actors. They could be evil manufacturers, state actors, patching problems. These systems often have to be maintained in an online status, and you don't have a separate copy of a manufacturing plant that you can go and test. So therefore, patching is often a problem because you have to wait maybe until the system is down, and sometimes the system is never down. So you have to incrementally try and find a way to patch the system without interfering with operations. Additionally, most of these systems were designed to work in isolations, and now that they're being connected to the internet, we have issues like Stuxnet, and feel free to Google that one if you haven't taken a course. It's referred to frequently in cyber-physical defense courses. And there's the protocol. A lot of these protocols are old. Again, a lot of that's just textbook stuff. However, they start to get into more detail, I think, which is beyond what you'll find in the college class. They talk about how the robots are interconnected with particular APIs, HTTP, of course, the internet. They talk about how robots themselves are no longer just software, are becoming more software-based. Traditionally, physical controls are being replaced with software controls, which are a little easier for malicious people to take advantage of. And they talk about robots that have been, what percentage of robots are actually customizable, what percentage are actually accessible from the internet, and whether it's FTP or other connections. And they go into a bit more detail in the document on how they do that with Shodan or other individuals who have surveyed the land already. Again, high level, looking at the general industry, what the general concerns are, and again, a priori thinking. They're not actually testing anything yet. They build an attacker profile, and for the most part, the assumption is that the attacker can't be just anybody. They have to have some knowledge. So that's a benefit, I think, to us. The attacker could be a casual attacker that works at the plant and has access to the firmware or to some component that they can modify, or potentially to some input or output. Or they could have access to and this is the scarier, or the more concerning issue, is that some of these systems are accessible to the internet. The robot itself could be accessed to the internet, and then you might be opening the door to more traditional network attacks. The target system here, and this is again a generalization, but it encompasses, from what I've seen in the presentation, the actual presentation on YouTube, it encompasses their learning from what they learned from looking at this particular robot. But also they have generalized it. A lot of these systems have similar components. This one, in general, they have sensory processing modules. These are the input and output, how the system or robot gains awareness of its environment. Knowledge modules, which is how the robot understands and models its environment. And then there are, as you kind of see, this is drilling down into even servo level or motor specific control and trajectory operational details. This could be, a matter of millimeters of control that is being performed by the actual robot. Another important piece, which you'll see later comes out in the attacks, is the teach pendant. A lot of the robots themselves have kind of human-robot interaction components. Teach pendant is how the operators can show the robot how to perform and behave, and we'll get into some more detail on that when we find that some of those teach pendants are in fact vulnerable to man-in-the-middle attacks. They go into quite a bit of detail on robot architecture. I just want to cover some key points. They can be offline and online. I think it's pretty straightforward. But in this case, actually, it's a bit different. Online refers to when someone is piloting the actual system, and offline is referring to when the robot is producing or is being programmed, which is important when you have certain attack scenarios where maybe the system, the operator might think that they're controlling the robot, and in fact there's a man in the middle or there's a corrupt system that is affecting that programming. Functional modes, automatic and manual. Automatic is where it's the production operational state, and manual is where the teach pendant is being used. Automatic is often very fast, and these are robots that are designed, clearly superhuman, with superhuman capacity, so they can perform things more quickly and fast, and also more powerfully at times. So that then becomes a danger if these things are hacked. And then there are what I think is pretty critical here, how they define a robot-specific attack, or these essential functional requirements that, and this is where all of their vulnerability assessments really come from in the next few slides. It's looking at exactly what is the robot trying to do, and this is then and kind of categorizing them according to accuracy. The robot is often trying to do something in terms of reading or producing precise values, knowing where its arm is at a particular point in time. There are often safety controls, and that's categorized by ISO engineering standards, and there are integrity controls, which mean effectively that the robot is designed in such a way as to not damage or internally collapse on itself. But of course, attackers are interested in violating those rules and any three of those rules. Okay, so they go into quite a bit of detail on potential vulnerabilities, and this really gives you a good feel for how the system and the robots are architected as well. At the servo level, these are these little motors that move the arm. You can potentially, attackers can potentially take out the control loop, and that could then affect safety or functional requirements for the robot. Could destroy the robot, and they would effectively drop in a modified config file. David makes a clear point that these systems do not have tamper-proof control, so accessing and modifying these files is actually very, relatively easy to perform. They cover a number of other potential vulnerabilities, the adjustments to the calibration parameters, and this is where the sensory processing or the knowledge models being affected. And again, these are files that would be exposed to someone that they could modify and then affect how the robot behaves, because it might think its arm is to the right when in fact its arm may be sitting next to an operator. They can actually affect the logic directly, and this is looking at more how the robot is producing, or maybe there's a conveyor belt, as some of us have seen. The robot could be moving pallets from conveyor belt to conveyor belt, and this would be directly altering that logic. Then there's, I think, what are more interesting, the user perceived robot state and robot state alteration. That's where you directly affect the robot state, and then by doing so affect the integrity, or can damage the robot, cause it to collapse on itself, or you can affect the user perceived robot state alteration. So if you give the HMI or the operator the tablet and tell him that the robot is off when in fact it's on, he may perform some actions that could be dangerous to the environment. Okay, so what do they actually do? If you look at the bottom of the screen, there are the actual pictures of the robot that they performed an actual pen test on. It was kind of a capstone. They looked at the overall, high-level industry threats. They looked at the specific system and robot threats, and they actually executed here an experiment on this arm. It was an ABB robot arm. If you look at this actual diagram here, they break down what all of these parts are here. There's a contractor unit and drive unit, access computer. All of these are basically, equivalent of a motor system to actuate commands coming from a main computer, which in this case I believe is just a Windows CE system. They found, when assessing this system and also just kind of generally surveying, they found 3 robots with authentication services disabled. I believe these are the Shodan surveys, as well as industrial routers that were more or less open for individuals to route commands to the robot. These were accessible at times on the internet. So that's I've actually colored these red just to make it clear that these are what most companies would consider a high risk. It's because they're easily accessible and can have tragic consequences. They found, in fact, when they were doing Shodan assessments, they found 1,044 robots which were available and potentially could be vulnerable to authentication bypass, which would give control of the robot to people on the internet. And again, that's highlighted red because of the high risk. And for the most part, these first 2 points are just kind of the high-level investigation they conducted. But when they actually performed the penetration test, the remainder of the findings are related to this particular robot. Where they demonstrated you paid $75,000, you could set up a robot in a lab and potentially experiment and find ways to break it and alter, your competitor or create damage to some process in a nation state. I think that's important too, because that cost is not something most of us can afford, but it is something that in this kind of reverse engineering process would be available to nation states or to malicious organizations that were dead set on destroying competitors. So now I'm kind of drilling down, I think, into the actual findings from the penetration test, and for the most part, a lot of these are very common. I think you'll find these in a lot of systems. Just having come from this field, things like USB ports and bus operators, remote access options were all available on this particular system, so that people could try to talk to the system or potentially interfere with how the system operates. And that kind of thing is not necessarily a high risk, but it could be a high risk, or it could be used to create a higher risk. And it is a vulnerability. They did identify that the FTP system was exposed, so individuals could read and modify configuration. That's a bit more concerning. And they found multiple masquerade and command injection vulnerabilities. And I think this is where things become, again, more concerning, that they could actually potentially authenticate and control the robot because, authentication is actually disabled on certain components on the robot, or the credentials are themselves hard-coded. And I think any of you that are in the security business would agree that this is a very frequent and common issue, because I think organizations that are developing software get lazy, and you'll find a lot of hard-coded credentials or poor authentication systems are out there when companies just choose not to invest in security that is generally necessary for systems to be operational. Weak encryption, again, another common security concern. It's not a high risk, although it could be if you could show that the robot itself could be modified. In any case, that's what they find later. The usernames and passwords were protected using bitwise or XOR operation. It's very trivial. Any of us could Google how to break that. Other encryption was actually being performed to protect safety, critical configuration, or some of the root core code. And that, of course, could be undone and reverse engineered. And then there were textbook Stack Overflow weaknesses. I think most of us are familiar with these, but it's something that you can use, to take or hijack the operating system by simply injecting instructional code into where you would expect to find data in memory. Additionally, there were code signature concerns. So the flex pendant controller, and the way that was connected to the main processor, there was no signature. So anyone could effectively implement a man-in-the-middle attack if they were to perform either physically interrupt the communication or perform, say, ARP spoofing on some of these components. There were And again, we have two high risks here. There were high risks associated with the Yumi cobot, which existed in the same space as the personnel. And what the attacker showed was that the manual and the automatic modes, which we talked about earlier, could be effectively swapped with a teaching pendant. And the result of which is that, you could, if attacker is able to put the actual robot into an operational mode when it's being programmed and potentially being serviced by an operator, you then have a direct risk to that operator. The operator could be killed or harmed by that robotic arm. In fact, they actually demonstrated that same, they could also change the .NET assemblies or overwrite the firmware itself, also creating safety risks to the workers who might believe it's in a safe operational mode when it's not. And they also demonstrated they could easily bypass some of the control routines, modifying the control loop and the calibration parameters. We had talked about the control loop attack, I believe earlier in slide 9, where again these configuration files are left more or less just sitting there in the open for anyone to change them that has a little bit of knowledge. And finally, they demonstrated that I think this is more general, none of the industrial robot safety standards that they've reviewed addressed any of these cybersecurity or adversarial control threats. They might have, and I saw this in the video, they might have addressed, safety concerns in general, but they did not address, how to take safeguards to ensure that the configuration files are protected. So what was learned? Okay, the fun part clearly was going in and hijacking these robots. But they wanted to leave everyone with kind of recommendations moving forward. So that the paper ends more or less with these recommendations. First, they don't recommend depending on human controls to manage, let's say, emergency situations, because often the robot reaction time is much quicker than humans, or there may be vulnerable HMIs. Secondly, they recommend that they recommend research to look at threat detection that's unique to these systems. They recommend also hardening of the operating systems. Often these are just kind of real-time operating systems that do not have compiler or memory canaries or controls to prevent hijacking of the system. So they recommend trying to, basically building controls around those systems. They recommend a number of STL software development controls, eliminating the debug components. Often the debug components, which are intended for testing the system, are left open in production systems, or in production systems, they found that they could access the actual C libraries directly on the system. So they recommended actually disabling those points of access. We're limiting setting credentials. We talked about that. We talked about the lack of password encryption and the lack of software encryption. So they recommend just eliminating that and getting instead actual encryption, standard encryption, rather than I assume the cheaper stuff. And then network controls. They recommend, this is I think key, they recommend actually making sure that all the components are not trusted. So you build the components in such a way that they have to authenticate with each other on the network in order to confirm that the components are actually the true components, and that comes out of that Industry 4.0 standard. Code signing is somewhat related. This is where you're ensuring that there are no man-in-the-middle attacks because the code has been signed, or at least a man-in-the-middle attack where that isn't capable of spoofing those signatures would be unsuccessful. Finally, sandboxing to separate the custom portions of the system where you want your customers to actually be able to modify and implement the system in their factory, separating those out from the core systems, which was not done appropriately in systems that were assessed. And finally, for the actual switching between automatic and manual modes, requiring code signatures or additional controls for those points. To conclude, they recommended some future research. They recommended that the industry explore a bit more around the wireless communications component. They didn't get into too much detail on that, but they realized that was a huge concern, especially as these robots, cobots, which are robots that interact with humans, are kind of added into a wireless network framework. So what are the implications of that? What are the security implications? Is there something unique to wireless versus having those systems wired that needs to be explored? I think any of us who've done any spoofing on a network can see how that could be a potential threat. Surveys and analysis, so clearly they were only looking at one system, but they would recommend moving forward that others contribute and potentially involve additional vendors, so they could get a better feel for the big picture. And with that, I'll conclude, and feel free, if you have any questions, to post them on YouTube or within Georgia Tech on our internal bulletin boards. Definitely did enjoy, again, this particular presentation, this particular report, and I hope that some of you do as well. And I also encourage you to look up David Quarta's actual presentation online. You'll find just additional, I tried to include some of those details, but you'll find probably additional details that I just could not include here. Thank you.